In 1972, the RAND Corporation put forward a competing transit method against aircraft and vehicles that could potentially alleviate the pollution involved with the ever-growing transportation industry across the globe. Rather than relying on fantastical ideas, the RAND Corporation approached the problem realistically, using technologies and methods available at the time. In this video, I hope to explain the company's analysis, authored by late engineer Robert M. Salter, both in its original context and with a modern perspective. The publication acknowledges that in the preceding 20 years, automobiles made up around 90% of travel between cities, predicted at the time to decrease as mass transit became more prevalent. A massive underground tunnel, dubbed the Very High-Speed Transit System, or VHST, was instead proposed. It envisioned passengers transferring directly from a local subway to a cross-continental train in the same terminal. The trains would then travel hundreds of miles below the surface, potentially faster than the speed of sound. Using over 1,000,000 amperes of current to generate the magnetic fields needed to levitate the VHST cars off of the track, the idea aims to create a power-conserving system that recycles the energy used to accelerate the cars. For a direct trip between New York City and Los Angeles, the train would follow Earth's curvature below the surface, taking under half an hour to cross the continent, while coasting nearly the entire way after a short period of acceleration. All energy put into acceleration is returned to the system while the vehicles are decelerated, thus being a highly efficient energy loop. The considerable expense associated with the construction of the tunnels would mean no long direct links across the continent at first. A system of hubs, linkage points, would be crucial in immediate steps of developing a coast-to-coast system. Chicago and Amarillo, with subsidiary lines to cities like Denver, Houston, Minneapolis, and an East Coast corridor, would likely be the main stopovers until the completion of direct routes. Two of the most significant issues with aircraft, and more significantly supersonic aircraft, are the pollution created and unrecoverable energy expended. Lift and thrust in aircraft use energy that cannot be used again. Once the fuel is burned, it cannot be recovered. RAND acknowledges that underground transportation alleviates many of these issues and suggests that moving to the proposed system could further avoid problems commonly associated with surface travel. An all-electric, energy-conserving system would not expel pollutants into the atmosphere, most especially when below the ground. Right-of-way costs, which were a considerable share of the interstate highway system's expenditures and can be avoided underground, required $16 billion by 1991, or 13% of the entire system's budget. This is even more obvious when you look at the most expensive stretches of the interstate, such as I-95 and I-75, neither of which are in the top 5 longest routes. A VHST system could also avoid grade and elevation issues faced by conventional road and rail systems. Salter even includes a statement saying that there was less chance of deadly sabotage, though this was well before 9/11, so a note should be made when acknowledging that potential benefit. Salter's publication determines that short distances are best suited for underground travel, such as intracity transportation. Medium-distance travel, such as within states or across a local region, cannot justify underground transportation as the cost would outweigh the demand in nearly all regions, excluding megalopolies such as the Northeast Corridor. The question, then, is whether long-distance travel would be justifiable for being moved underground. RAND's research shows that long-haul underground transportation can pay for itself. However, to do so, it must operate at very high speeds and work with other public transit systems, people movers, subways, and buses, and potentially public utilities. Unlike other forms of travel, VHST would be unaffected by above-ground weather. Travel times and costs could be significantly reduced, with a trip from Boston to San Francisco potentially being under an hour if using stopovers. RAND estimates that trains carrying 100 passengers each could move up to 300,000 people daily, over 100 million people a year. This is about half of 1972's total air traffic, though, with each passenger paying hundreds or thousands of dollars per flight. The VHST system, on the other hand, could potentially bring the cost of a cross-country trip to under $50. creating a demand for more than 100 million people it could initially carry and yielding over $5.3 billion a year. Estimated to cost $90 billion for the central corridor between New York City and Los Angeles, or $30 million per mile, the line could be paid off in 30 years and likely less if costs can be reduced with rising demand. Freight transport, another possibility of the system, could be done at 1 cent per ton mile and can move over 7 million tons across the country daily at greater speeds than ever before achievable. Salter believes that one of the most demanding problems with developing the system is lateral or sideways acceleration. Sharp turns at speeds of up to and over 500 miles per hour are simply not possible. A track's bend at that speed requires a 4-mile radius, and for speeds over 5,000 miles per hour, which the system is said to be able to eventually achieve, a 400-mile radius is needed. Thankfully, much of this difficulty can be overcome as a result of the depth of the track. Being hundreds of miles underground, there would be no issues with grade crossings, right-of-way costs, and routing about obstacles. Another problem also exists. Over 90% of the costs associated with the system are likely to be from the tunnel's development, even if very expensive hardware is to be used for the actual train. More sophisticated systems should be incorporated if they can alleviate costs, including increased system capacity. Unfortunately, neither of these solutions addresses the most significant issue. High speeds required by the train are simply unobtainable with conventional methods, even magnetic levitation or maglev. High precision is demanded. Only the most minor deviations from the plan are permitted, and continuous correction is required throughout the track. At mile 427, for example, the design might call for speeds of 723 miles per hour while thrusting at 47.8 degrees with a force of 1.38 Gs. Every car passing this point must meet these metrics every time with minimal tolerance. However, if the thrust vector is carefully matched at every point, the system could yield high efficiency. The system would work with large superconductors that raise the cars 1 foot off of the track. The superconducting loop in the car opposes the track's conductors, which are heavy bus bars whose currents levitate, propel, control, and slow the vehicle. Cryogenic fluids, used to keep the vehicle's conductors at supercool temperatures, would be refilled at terminal points, while boil-off would be stored to be recycled. Powerful electromagnetic waves would be the driver of the train cars, of which one of 2 wave types would be used, each with its own trade-offs. The most effective waveform is a traveling wave, but this requires triggering circuits and pulse-forming networks, making the system more complex. Alternatively, standing waves require less electronic hardware but need, on average, twice the amount of current that traveling waves need. Additional trade-offs exist with the high amount of air present in the tunnel, which would need to be at least a partial vacuum. A high vacuum environment, requiring significant amounts of power and expensive diffusion or ion pumps to achieve, would be unnecessary. No vacuum, though, would result in drag and heating issues. A compromise RAND proposes is using 2 vacuum roughing pumps every mile, reducing the pressure to just 0.5 millimeters of mercury, equivalent to about 170,000 feet in altitude. Putting the numbers together, a pump down to the required pressure in 9 hours for 5,000 miles of tunnel would cost about $78 million. A vacuum requirement also eliminates the need for streamlining train cars, and instead a heat shield would be incorporated in the event of a significant leak in the tunnel. Pumping would even consider leakage that would be present, estimated to normally leak at 77 liters per second per mile of tunnel. Power to maintain the vacuum would be non-negotiable, and this is the most crucial aspect to keep running, alongside the train's control systems. Both systems would require similar amounts of energy, though costs are still small compared to potential revenues. Final designs might require cooling the cars to deal with heat issues associated with being deep underground and the great velocities. If needed, a self-contained heat reservoir could be used and recharged at stoppage points. These points must have quick opening gates and differential pumping to maintain the tube's vacuum as well. One method proposed would have large doors closed on each side of the train, time for arrivals, to maintain the vacuum in the tunnel. As mentioned previously, lateral acceleration is one of the most challenging problems in a VHST system, despite the many issues avoided by being underground. Considering the choice of tunneling, it would not only help with our rising contribution to greenhouse gas emissions, but tunneling technology could offer great potential for alleviating many problems that come with urbanization, such as the increasing dependency on cars. Tunneling costs are challenging to estimate, given the industry's ever-evolving technology. A study referenced by RAND's analysis and published by the DOT's Office of High-Speed Ground Transportation suggested that future demand would reduce costs by 30 to 50%, and advancement rates in technology would increase by 2 to 300%. New techniques to improve excavation, tunnel support installations, transportation of excavated rubble out of and materials and personnel into the tunnel would reduce the time and costs associated with construction. With the technology available in 1972, Salter dove into the feasibility that the most used methods would provide. Rotary machines demonstrate rates of 10 meters per day for 10-meter diameter holes. However, they also sometimes require more than 50% downtime and face issues with igneous and other hard rocks. Explosives used in shaped charge blasting showed good promise, though are slow-moving and involve higher risks. Flame jet drills, lasers, electron beams, and acoustic transducers have even been proposed. These all have high energy requirements though, and can also encounter difficulties with igneous formations. One issue all drilling methods present though is the problem of debris removal, especially for faster drills. The most promising of the drilling techniques available in 1972 was a rock melting drill, which provides its own debris removal. Under investigation at the Los Alamos Scientific Laboratory, a rock melting drill would have the highest advancement rate at over 100 meters per day, would be efficient on most rocks, especially igneous, would not rotate, and would even create an outer lining of strong glass-like material. The latter, the glass material, could even be used to ensure no need for shoring up tunnel walls during construction and provide a pressure-tight, impervious lining. Nuclear power would provide the energy, being compact and self-contained. 50 megawatts would be required based on melting 25% of the tunnel, an annular region with the core being removed physically. The drill would be made of tungsten or zirconium alloy and could use laser systems for guidance and telemetry. Rand concluded this section by claiming the most appropriate and efficient method could be determined given which drilling method is needed with a specific type of rock to bore through. This would, though, require a vast expansion of our mapping of underground geologic formations. A smaller version of a subterrane could be used to drill test holes, though. Tunnel lining is required for each drilling method, excluding the rock melting drill, which provides its own lining. For other methods, pre-stressed high-strength concrete, likely rated at over 10,000 pounds per square inch, is the probable candidate. Distributed polymers and irradiation would help strengthen the bonding. 9-foot concrete pipes, which were used for the Feather River Water Project in California, cost $182 per foot, meaning for the proposed VHST system, a 5,000-mile vacuum shell would require $5 billion of concrete. One of the more interesting results of Salter's analysis shows Rand Corp's own studies of tunnels indicate that, excluding the additional lifts used for moving debris to the surface, there should be little difference between drilling a mile deep versus 200 feet deep. This conclusion is drawn from the idea that greater depths will be more consistent in rock type and, as described in the mining industry, competent or easier to bore through without support mechanisms. This means it could even be possible to tunnel under deep bodies of water. A route from Seattle to Paris following a Great Circle path would not require any deep ocean tunneling, with the maximum depth not exceeding a mile, as it passes under Canada, Greenland, Iceland, and relatively shallow waters. The development of a very high-speed transportation system offers the potential for a coexisting freight transport system, dubbed by Rand as the Fast Rail System, or FRS. It could carry semi-trailers, containers, campers, and other items that are too bulky for railway cars designed to carry passengers. FRS could consist of a transcontinental link with additional crosslinks, and though it would be on the same advanced rail, the trains would only likely travel at 100 miles per hour. Electrically driven, a coast-to-coast trip would only take a day, and trains could carry around a dozen cars, each large enough to hold a standard surface railroad car. To travel at 100 miles per hour, the train would require about 100 horsepower per car, equally driven by rolling and air friction. Wheeled support is best at this speed and for this purpose, though traced air cushion vehicles or TACVs might be cost effective with the trade-off of less power consumption against greater investment demands. Several hundred horsepower per car would be required for acceleration to 100 miles per hour, which could be primarily obtained by using gravity from loading yards. RAND calculates a 300-foot drop would be needed to accelerate and a similar rise at the end of the trip to decelerate. Added constraints on rail facilities, though, might be more costly than simply installing the additional power needed without gravity acceleration. To load the FRS cars, marshalling yards would be used as station points, and cars would even be connected to form trains at lengths sufficient to reduce air resistance. Trains could even be reformed during transit with slight speed changes to isolate either a slot between cars or discharge a car entirely from the train, with input and output maneuvers near cities. This would make FRS available to more remote areas that wouldn't have an easily accessible passenger terminal. Overall, this idea could radically reduce the need for transcontinental trucking and possibly bring down air freight demands. In its concluding remarks, the RAND Corporation makes several positive affirmations in favor of developing and constructing a very high-speed transportation system. It could spend less time traveling coast to coast than the time needed to go to an airport, board a plane, and reach a cruising altitude. Efficient electrical drives that allow for the recovery of most of the energy and incorporation with existing transportation and utility systems would bring down costs and reduce average expenses. On top of this, the environment benefits both because of this conserved energy and because of the lack of exhaust and noise pollution that other transport methods create. Technical problems are broad and challenging, but no scientific breakthroughs are required. Instead, heavy investment and significant development of existing technologies would be needed. Critical areas left to solve include precise tunnel alignment, lateral acceleration, vehicle control and damping, and solving the best method of boring the tunnel. The Ralph M. Parsons Company undertook a comprehensive analysis of the proposal's feasibility. Assuming the drill and blast method is best suited for most of the route, shaped charges placed in pilot holes would be used in conjunction. Dedicated power stations would also be needed, with the study interestingly noting that the cost between fossil fuels and nuclear power were comparable. The RAND Corporation did not comment, though, on whether the Ralph M. Parsons analysis studied the differences between the two in terms of pollution output, though it can be assumed that fossil fuels would greatly outweigh nuclear power. The Parsons analysis concludes by stating that a VHST system would have to pay for itself with high traffic volume. The electricity needed alone would cost less than $1 per passenger trip, and a $50 fare per passenger might be reduced to under $10 if the traffic volume increases tenfold. Salter acknowledges future demands on the system cannot be accurately forecast. However, studies do indicate that with the transportation abilities offered by a VHST system, demand would be high. For example, a New Yorker could simply get off of the city's subway and onto a train, arriving in LA in less time than it would take to simply get to JFK Airport and to their gate. RAND even goes as far as expanding the idea globally, claiming a system may eventually be able to cross under the Bering Strait and through the North Sea, under Greenland and Iceland. Salter finally asks three compelling questions about the VHST concept. First, will such a system ever be developed? Answering his own question, he concluded that, quote, the political outlook is much less optimistic than the technical one. Tunneling, for starters, poses legal issues over subverting border restrictions. Napoleon is well known for suggesting the idea of tunneling beneath the English Channel in 1802, going as far as having professional surveys and proposals done for the project. Though, born of hostilities, his idea for a channel tunnel would be delayed for nearly 2 centuries thanks to enduring political and financial pressures. Alternatively, Rand acknowledges that relatively primitive societies achieved feats such as the Great Pyramids. Theoretically, the ancient Egyptians probably would have felt a much greater economic impact than a VHST system would have on us today. The proposal's second question asks, are there compelling reasons for a VHST system? Emphatically answering yes, Salter acknowledges climate change as an inevitable consequence of our own polluting activities. carbon, chemical, light, and noise pollution, along with carving up wilderness and arable land, wasting limited fossil fuels, and increasing auto traffic rates, have all contributed to the observable and measurable fact that the Earth is warming and we are the cause. In the search for ways to counteract these increasing global trajectories, a system like this might just bring us one step closer to solving the problem. Rand finishes its answer by stating that another need for such a transit system is to restore to motorists the pleasure and convenience of driving through the countryside. Is the VHST system really far-fetched? Salter asks this final question concerning the proposed project. Looking back over the last 100 years of transportation, Salter mentions how we've come incredibly far in the development of transit technology. Not mentioned in the PDF, but in the century preceding this article, people saw the development of cars and the first powered flight soon escalate to global flights and putting a man on the moon for the first time just 3 years earlier. However, Salter argues that little to no similar significant attempts to integrate transportation methods have been made. A VHST system could be specifically designed to be integrated with existing and proposed public transportation systems. Even local utility companies and transport districts could plan to merge the system into their own existing infrastructure. When looking back over the 50 years since Salter's article was first published, it's interesting to think of all that's changed and all that hasn't in that time. Space hasn't really taken mankind further than the moon, except in the form of probes which have done impressive things, as I've highlighted in other videos of mine. Airplane technology has significantly developed in the fields of efficiency and passenger safety, but with the absence of Concorde and any successor, average flight times haven't dropped in decades. It takes just as long to fly from New York to London as it did 50 years ago, if not longer, with the added security checks. And while some countries have taken great strides to develop their high-speed railways, consistently reaching speeds of 200 miles per hour, the United States has dramatically fallen behind in developing what could be one of the engineering highlights of the world. To look over the proposal with today's technological and engineering developments, I believe we have to analyze 5 core pieces that make up the VHST system. First, the research and development of the train and tunnel would have today's modern materials and high-precision machining at its disposal, as well as advanced computers. While the main pieces of making the train physically possible, magnetic levitation, vacuum tunnels, and deep subterranean routing, were technically feasible in 1972, the idea relied heavily on concepts and machinery still in early development. Today, our progress makes the idea much more plausible, though still complex, with solutions that require ongoing refinement. Precision requirements for such a large-scale project still remain incredibly demanding, and further research is needed on tunneling methods like rock melting drills and boring autonomous systems. One notable absence from the RAND study is the concern of earthquakes and tectonic plates when traveling underground. Seismic activity, especially in places like along the San Andreas fault line, adds another layer of complexity, and any deep, long-distance tunneling would have to account for potential earthquakes that could severely damage the lines. When considering energy usage and the state of the climate from today's point of view, we can get a better understanding of how we're affecting our planet and design for a cleaner future. The VHST concept is just one possible concept and remains a relevant idea that's capable of offering high-speed transit without producing significant pollution. Many facts about the system still hold true, including the lack of greenhouse gas emissions and the elimination of noise pollution. The system, with today's technology, would likely even be more efficient than initially proposed. Efficiency coincides with cost, another significant point to consider. It was and remains the most significant barrier to implementation. Rand estimated in 1972 that a single corridor spanning 5,000 miles would cost around $90 billion. Today's price tag would be substantially higher. However, the return on investment through greater efficiency and high volume traffic could still make the system viable in just a few decades of operation. Another potential barrier to the development of this system is the politics surrounding such an idea, with Salter recognizing early on that the political challenges outweigh the technical ones. Issues of below-ground usage rights and obtaining public trust are all significant factors. Cross-border cooperation between counties, states, and potentially countries, each with their own sets of differing construction codes and laws related to the project, would not be easy to achieve. Projects at this scale will inevitably require long-term planning, immense bipartisan support, economic availability, and a shared vision for substantial infrastructure development. Though other points remain to be touched upon for a modern-day approach to the proposed system, how the VHST would work with modern-day infrastructure is the fifth central point I believe that needs to be examined. The VHST system was envisioned by Salter and Rand as a complement and expansion of existing transit systems, with the ability to directly integrate a multitude of methods of public transportation. Integration of these existing utilities is essential for utilizing the entire system to its full potential. However, significant adaptations would need to be completed to already built components to accommodate the proposed high-speed system. This presents its own set of logistical and engineering challenges, likely requiring an overhaul of modern-day small-scale transit infrastructure. High-density areas that have long established structures and utilities would be particularly difficult to adapt. I would like to believe that Salter would appreciate the progressing attempts by many countries that aim to be the first to produce his idea. I also want to believe that it will become a reality someday. Having the ability to travel globally at such speeds would completely change our outlook on our planet, our species, and how far we can go with our progress.